Okay, welcome to this lecture. So today we're gonna solve this problem here. So given a circle and a rectangle, we want to show that the area of the circle, so the area of this thing here, is larger than the area of the rectangle. Given that they have the same circumference. Okay, so let's start. So the first thing I'm gonna do is to create two figures. So we have a circle, and this circle have a diameter d, and the rectangle have sides x and y. And we know that the circumference of the circle is the same as the circumference of the rectangle. So let's express the circumference of the circle. So the circumference of the circle is the same as pi times the diameter, and the circumference of the rectangle are the same as x plus x plus y plus y. So we have x here, and y here. This equals to 2x plus 2y, and we can factor out the 2 and we get 2 times x plus y. Okay, so we can set the circumference of the circle equals to the circumference of the rectangle. So we have pi times d equals 2 times x plus y. So the reason for doing this is that I can now then express the diameter of the circle with respect to x and y. So we have d equals 2 times x plus y divided by pi. So this expression we're going to use in order to express the area of the circle and the area of the rectangle. So I have the area of the circle, which is the same as pi multiplied with a radius squared, which is the same as pi divided by 4 times the diameter squared, which is the same as pi divided by 4 times the expression here. So we have 2 times x plus y divided by pi squared. So this is the same as pi divided by 4 times 4 times x plus y squared divided by pi squared. Okay, so the 4 cancel out each other and pi here. So what we get is x plus y squared divided by pi. So this is the area of the circle expressed with x and y. And the area of the rectangle is x times y. Okay. So what we want to do now is actually to show that the area of the circle is larger than the area of the rectangle. Okay. And we want to show that for x larger than 0 and y larger than 0. So we don't want negative sides, and we don't want sides that are 0. So in order to show this here, we can compute a function. We call it dxy, which is the same as the difference of the areas. So the area of the circle subtracted with the area of the rectangle. And if we can show, so if we can, if we can show that this function dxy is larger than 0 for for all x and y larger than 0, then we have proven that the area of the circle must be larger than the area of the rectangle, right? Because the difference will be larger than 0. So we can express this function dxy, which is the same as x plus y squared divided by pi minus xy. Our next step is to compute the gradient vector in order to find the critical point. So I write gradient vector. So the gradient vector, I write this upside down triangle. The gradient vector of dxy is the same as taking the derivatives with respect to x and then with respect to y. So write d of dx and then d of dy. And this can be written more simply like this. So write dx dy. So this means that we are taking the derivative of function d with respect to x here, and then we take the derivative of the function d with respect to y here. And then we have to set it equals to 0. So the zero vector, to be more precise. Okay. So let's compute dx. So let's first write dxy, which is the same as x plus y squared divided by pi minus xy. So dx of xy will be the same as, so we are finding the derivative with respect to x, so y will be a constant. So we have 2 divided by pi. So the 2 here goes down here, right? So it becomes 2 divided by pi times x plus y, and then the inner derivative of x plus y becomes 1, and then minus, and the derivative of x times y, where y is a constant, we get y left, because the derivative of x is 1, and the derivative of y, so the derivative of d with respect to y is the same as 2 divided by pi times x plus y, but minus x. Okay. So now our gradient vector d x y becomes this. We have dx, right, and dy here. So it becomes, so dx is this expression here, so 2 divided by pi times x plus y minus y, and dy is this expression down here, so 2 divided by pi times x plus y minus x. Okay, and we want to set it equals to the 0 vector, so 0, 0. So that means we will get a system of linear equations. So we get 2 divided by pi times x plus y minus y equals to 0, and 2 divided by pi times x plus y minus x equals 0. So we have two unknowns, x and y, and two equations. So this system of linear equations can easily be solved by subtracting both equations with each other. So we will subtract this one with the lower one here. So those two cancel out each other, and left are minus y. So we have minus here and minus x. It becomes plus x equals 0. So we have that x equals y. So they are the same, but we don't have any values for x and y. So we have to find that. So we can just insert x equals y in the first equation. We can, for example, insert it here. And then we have 2 divided by pi times x. We say that x is y now, plus y minus y equals to 0. So we have 2 divided by pi times 2y minus y equals 0. And then if we factor out y, we get 2 divided by pi times 2 minus 1, which is 0. And then we can see that y have to be 0. Okay, so that means x have to be 0 also. So we have a critical point which is x and y, which is equals to 0, 0. Okay. So the next step is to determine if this critical point is a minimum point. So if it's a minimum point, so if this point is a minimum point, that means that the function d is a global minimum, because we have one critical point. So one global minimum point, and that means all other points close to this 0, 0 point is larger than this critical point. So that means that it has larger z values, so the difference is larger than the critical point. So we can see that, for example, if we insert d 0, 0, we can find out the difference of the areas, and of course it will be 0. So let's write it like this, x plus y. So let's write it like this first. So we have dx y, which is the same as x plus y squared divided by pi minus xy. So d 0, 0 is the same as 0 plus 0 squared divided by pi minus 0 times 0. So everything will be 0. So the difference of the area of the difference of the area of the circle and the area of the rectangle is actually 0. But remember that we are interested in x values larger than 0 and y values larger than 0. But if we find out that this critical point here is a minimum point, that means for all x larger than 0 and y larger than 0, we actually have a difference in area which is larger. So the difference in area will be larger than 0. Okay. So our next step is to actually perform a test to determine if the critical point is a minimum point or maximum point or a saddle point. So in order to do that, we have to introduce something called a Hessian matrix. So matrix. So the Hessian matrix H consists of computing something called partial derivatives. So I'm just going to write it out. So what it means is that we are computing the derivative of the function d with respect to x first, and then we take that result and compute the derivative again with respect to x. So for example, here we compute the derivative with respect to x first, and then followed by the derivative with respect of y. And here we start with y, and then we continue with x, and then we compute the derivative with respect to y, and then followed by y again. Okay. So the thing with this Hessian matrix, we can use this in a test to find out whether the critical point is a maximum, minimum, or a saddle point. So in order to do that, we have to compute the determinant of this Hessian matrix, which is the same as dxx. So the determinant of a matrix is the same as multiplying these elements with each other and then subtract with a multiplication of these two elements. So we have dxx times dyy subtracted with dxy times dyx, and they are the same here, so we get that the determinant of the Hessian matrix is dxx times dyy minus dxy squared. And then we can perform this test here. So test. So we have if the determinant of the Hessian matrix is larger than 0 and dxx is larger than 0, we will have a minimum point. Okay, I write it min. And if the determinant of the Hessian matrix is larger than 0 and dxx is smaller than 0, then we have a maximum point. Okay, but if we have the determinant of this Hessian matrix is smaller than 0, then we have a saddle point. Minimum point, maximum point. Okay, but if the determinant is equal to 0, the test is inconclusive, so we cannot know whether it's a minimum, maximum, or saddle point, so it can be any of those. So let's find out what these derivatives are. So we have dx is the same as what we computed here. Let's see. So dx is this thing here, and dy is this thing here. So just write it again. So it's 2 divided by pi, and then let's see here, times x plus y minus y, and dy is the same as 2 divided by pi times x plus y minus x. And then we take the derivative of this function again, so we have dxx, which is the same as, so we have to find the derivative of this function with respect to x again, so we have 2 divided by pi. So this thing becomes 0, and this is multiplied with x, so we have 2 divided by pi, because the derivative of x is 1, and then the derivative of y is 0. So dxx is 2 over pi, so dyy is the same as 2 over pi again, and then we have to compute dxy. So we can take this one here, the first one, and now we have to find the derivative in respect to y. So we have 2 divided by pi minus 1. Okay, and then we can compute the determinant of the Hessian matrix. So the Hessian matrix, so let's write the Hessian matrix. The Hessian matrix is the same as dxx is 2 over pi, and then we have dyy, which is 2 over pi, and then we have dxy and dyx are the same, so 2 over pi minus 1 and 2 over pi minus 1. So like this. Okay, so the determinant is the same as this one multiplied with this one, so we have 4 divided by pi squared. So let's write the whole expression like this. So we have dxx times dyy minus dxy squared. So we have 2 over pi. So dxx is this thing here, so it's 2 over pi times dyy, which is this one, 2 over pi, minus this one squared, so 2 over pi minus 1 squared. So I have pre-computed it before, so it's 0.27. Okay, so the determinant, we have that, okay, we have that determinant of the Hessian matrix is larger than 0, and we have dxx larger than 0 because 2 over pi is larger than 0 because we have 2 divided by 3.14, right? So this is obviously larger than 0. So this means that we have a minimum point. So the point 0, 0 is a minimum point. So this means that dxy is larger than 0 for all x larger than 0 and y larger than 0, which means that the area of the circle is larger than the area of the rectangle. Okay, so we have now proven this by using gradient vectors. So first we express the difference in area between the area of the circle and the area of the rectangle, and then we compute this d function, which is the difference between the area of the circle and area of the rectangle, and then we use gradient vectors to find the critical points, followed by computing the determinant of the Hessian matrix in order to perform the test to determine if the critical point is a minimum, maximum, or a saddle point, and in this case it's a minimum point. If you enjoyed this video, please subscribe and like this video. So the solution to the problem will be uploaded in the website, which I will link to in the description. Thank you for listening. See you in the next video.